Great. Thanks, Gemma. So as a geotechnical engineer with BGC and engineer of record for two tailings facilities, I'm very excited to be introducing the next presentation. Um, Risk-informed decision making is becoming more common, but also much more expected within mining and tailings projects in practice. And while the practice of reducing risk is not new and our design process has always strived for this, there's increasing demand to quantify risk to help in making and justifying decisions. This is due in part to the requirements of the Global Tailings Standard, but it's also been ingrained within CDA and MAC guidelines for years. But the mining industry faces some challenges with adjusting to adopt more risk-informed decision making, including establishing common understanding of many risk concepts, but also in developing and establishing consistent and accepted methods to estimate risk. BGC is excited to have Michael Porter working with our mining team and our clients to help broaden the understanding of risk and develop tools to help tailings and mining practitioners become more versed in risk-based methods to make some of these decisions. Mike is a BGC director and principal geological engineer with a broad background in engineering geology and geotechnical engineering. Mike's technical focus has been on development and implementation of geohazard risk management programs for oil and gas, hydropower, transportation, and mining industries. He's a co-author of the Canadian Technical Guidelines on Landslides, an author of over 60 technical papers on topics ranging from numerical modeling of mine pit slope deformations to the investigation, risk assessment, and remediation of landslides and other natural hazards. With that, I'll turn it over to you, Mike.
Okay, yeah, thank you very much, Brad. And let's just see if I can figure out how to advance my slides here. There we go. Yeah, so as Brad hinted at, ultimately where we're going to get to in this presentation is to introduce an approach that we've been working on to estimate the probability of tailings dam failures. And this is an approach that's intended to complement other expert-based approaches, including failure mode analysis and semi-quantitative risk assessment. But to begin, though, I'd like to begin by reviewing some concepts just related to uncertainty, probability, and risk, and risk-informed decision-making. And this will be kind of review for most of you, probably nothing that you haven't heard before, but I think it's just helpful to have this kind of fresh in your minds as we go through the next part of the presentation. So risk-informed decision-making, it's an approach to achieving objectives while balancing costs and benefits in the face of uncertainty. And one application of risk-informed decision-making that many of us are quite familiar with is where we look at comparing risk estimates to risk tolerance criteria. And that is a fairly narrow application of risk-informed decision-making. It's an important one, but I think there are other applications that offer greater value, and I've listed a few of those here. So some of these include clarifying decision-making processes, selecting preferred options, and optimizing solutions. So risk is a word that we use a lot. It carries different meanings in our common language. But the definition that's listed here is the one that I prefer, and that is that risk is a measure of the effects of uncertainty on objectives. So one of the ways that we measure risk or quantify risk is we look at the probability and consequence of different scenarios. And what that provides us with is it's an estimate of the risk or the expected value for a different scenario. And we can do that with a calculator, but in reality, we all estimate risk all of the time. And in most situations, we've actually evolved to be so good at this that we don't even realize we're doing it. It's done subconsciously, and that's something that's served us very well. But occasionally, and especially in today's modern world, our instinctive approach to estimating risk can get us into trouble. And again, I've listed a few of the reasons why that is. We tend in our work to deal with relatively low probability, high consequence events. That makes it difficult to become well calibrated. We're often dealing with systems that are very tightly coupled, and we can't always directly see what's going on, and so that makes risk assessment challenging. And we also deal with statistical distribution of model parameters that are not normally distributed often. They have these fat tails, which is a way of saying that things that seem like they're extremely unlikely, they just have a way of happening more frequently than we might expect. And I also wanted to note that unfortunately there's no evolutionary advantage to being really good at estimating geotechnical risk, or at least none that I'm aware of. And so what that means is that future generations aren't going to have any better instincts about these types of risks than we do, and that means that we're going to continue to need to learn these skills, and hopefully through better mentoring and training, we can help others advance through that process more quickly. Uncertainty is another word that gets tossed around quite a bit, what I take uncertainty to be is just the existence of more than one possibility, and it arises in part just out of randomness. But more importantly, it's really because we have imperfect knowledge, and so probability is just a way of expressing a measure or a quantification of our uncertainty. And so if we're 99% certain of something, that means we're 1% uncertain. That's like saying we're 99% confident that something is true, and there's a 1% chance it's false. So there are two types of probability that we deal with. There's the frequentist definition of probability, and the degree of belief in a hypothesis. And so frequentist probabilities can be assigned to repeatable objective processes. And when we look at systems and aggregates, their behavior sometimes resembles repeatable objective processes. And when that's so, we can use observations of event occurrences to assign frequencies or probabilities. But in most real-world problems of significance, and certainly when we're dealing with a site-specific, engineering scale type problem, what we usually rely on are these degree of belief probabilities. And as an example of that, the average Canadian rate of average rate that Canadians die in car accidents is an objective, repeatable process that can be measured. But the probability that you or I might die in a car accident next year is not, and I guess that's a good thing. And certainly the risk that you or I face, it might be quite different than the average Canadians because of driving habits and other things, and we take that into consideration, when we make decisions. So these degree of belief probabilities, they're not a physical property of a system. Physical properties might influence our degree of belief, but what these degree of belief probabilities are is an expression of our state of knowledge and our confidence of how a system might perform in the future. And even if there's no physical change in that system, our beliefs and our estimates of probability will change when we're presented with new information. And so while these types of probability that we're dealing with, they're not countable, kind of tangible things, they're incredibly important. And the reason they're important is that because, for better or worse, every decision we make is based on our belief in a hypothesis. And so, unless you spend your entire life in a casino where maybe, these frequentist type probabilities are more applicable, it's likely that most of the important decisions you make in your life will be made on a subjective degree of belief probability. So hopefully we all agree that the failure of a specific tailings dam is not an objective, repeatable process. Our assessment of the probability of failure is influenced by our knowledge and our beliefs. And our estimates of probability will change if conditions change, or if we are presented with new information. And I think it's also important to note that all these things are subjective. Some estimates of probability of failure are more reasonable and more defensible than others. And using more reasonable estimates will typically lead to better decisions. So the most common practice for estimating the probability of failure of a tailings dam is through a failure modes analysis and expert-based semi-quantitative risk assessments. And this is a very valuable approach. It's valuable because in the process of conducting a risk assessment this way, there's an opportunity to discover deficiencies in the design or operational practices. And then these become things that that we can do to further reduce uncertainty and risk. And that's very useful and something that I think we need to keep doing. But there are also a number of challenges associated with estimating probability of failure this way. And again, I've listed some of those challenges here. So for example, it's very hard for experts to assign probabilities to unknowns using this sort of approach. And also, experts, like everyone, are subject to bias. And even when you're subject to these biases, they can be challenging to overcome. So to help overcome some of these challenges with assigning probabilities of failure to tailings dams, Brad Russell and Brian Watts and I have been working on a complementary approach. And this is something that we'll be presenting at the Tailings and Mine Waste Conference here in Vancouver in November. And our approach begins with estimates of the average probabilities of failure for different dam raise methods. And these estimates are based on reported failures over about the last 25 years. And an assumption that those failures were derived from a total population of about 20,000 tailings dams. And so our suspicion is that there are probably more dams in the world than that, but also that the total number of reported failures is incomplete. And so those potential errors, we expect that they cancel out. And so for now, anyway, we believe this is a reasonable estimate. So the average probability of failure that we're reporting here, it's something that reflects the poor performance of a relatively small number of dams. And so we believe that the median or the typical probability of failure for a tailings dam is potentially much lower than the average values that are reported here. So we've estimated the average probability of tailings dam failures by raise method, and then we took this one step further, and that's to estimate the average probability of failure for the different common failure modes. So we did this by leveraging interpretations of the failure databases that have been made by a number of different researchers, including those that are reported by Stark and colleagues in a 2022 paper. And so what we're showing here is a breakdown of an estimate of the number of tailings dam failures in percentage form by mode. And so it's a pretty simple exercise once you have that and the estimated total average probability of failure to come up with a probability of failure for each failure mode. And that's what we're showing here. And so these average failure mode probabilities then form kind of the foundation for the approach that Brad and Brian and I have been working on. So then what we asked ourselves is, for each of these credible failure modes, what makes a specific dam more or less likely to fail than the average? And we considered 3 different criteria: site factors, governance, and design practice. And we used these criteria to help adjust the average probability of failure for each of these failure modes up or down, and then sum up the results to get an estimate of the total probability of failure. So site factors are the project constraints and natural conditions that are present at a site. So these will include things like the geology, the topography, the seismicity, and the climate. And these are conditions that we can't change, or at least can't change very easily. But they can have an impact on the credibility and likelihood of the different failure modes. So these are the sorts of things that our designs and our governance practices need to account for. And what we do with these site factors is we simply adjust the probability of each failure mode up or down by as much as a half order of magnitude if the site conditions appear to be either more adverse or more favorable than we expect them to be on average. So governance or level of practice, this is what enables us to detect and address uncertainties, errors, and changing conditions during design, construction, operation, and closure of a tailings dam. And we believe, and I think everyone would agree, that with good governance practice, you can dramatically reduce the likelihood of a tailings dam failure. So to account for this level of practice, we borrowed some ideas by Siobhan and others who developed an approach to ranking different areas of governance practice. And in their approach, they related this scoring method to a slope stability factor of safety and used that to estimate the probability of failure. So our approach differs slightly in that we are assessing a level of governance practice for each of the credible failure modes that have been identified. And then we don't explicitly link that to a slope stability factor of safety to adjust the failure mode probabilities. Instead, what we do is where we judge the governance practice to be poor, we increase the average failure mode probability by another half order of magnitude. And where we judge the level of practice to be good or high, we decrease the failure mode probability by up to 1 order of magnitude. And lastly, we consider design practice, and what this includes is the design basis and the key design approaches that are taken to manage uncertainty and risk. And so, for example, this would be things like, does the design accommodate the maximum credible earthquake and the maximum probable flood? And again, we've done this for each of the common failure modes and laid out a series of criteria that certainly in the opinions of Brad and Brian are key things that need to be done to manage risk for these structures. And so for the failure modes where these key criteria have been met, again, we reduce the failure mode probability by another order of magnitude. Just looking at the time here, I think I'm doing okay. So this is something I left to the very end because it's a little bit of a tangent, but and I wasn't sure if I'd have time for it, but and maybe we should have stated this up front, but a key objective of risk-informed decision making in tailings practice is that there's a need to eliminate fatalities from tailings dam failures. And that raises the question, what then is safe if the goal is zero fatalities? And I guess that the main point that I wanted to make here is that we don't make dams safe by assigning incredibly low probabilities of failure to them. We make them safe through good engineering practice, by demonstrating that the probability of failure is reasonably low. And then by putting all these measures in place to keep that level of risk under review and to make sure that the conditions change. And so, if someone estimates that the probability of a tailings dam failure is 1 in a million, 10 to the minus 6, and then it happens to fail a few years later, it's not that we should have tried to get the failure probability down to 10 to the minus 8. It's that we probably missed something really important, some deficiency, and so that's really where the effort needs to be. It's not driving these probabilities of failure down to indefensibly low numbers, but making sure that we have confidence in the safety of these dams. And that brings me to the end of the presentation. We're continuing to work on advancing this model through calibration, and a lot of what is in here in terms of these adjustment factors are based on the expert opinions of folks like Brad and Brian. We would really like to take more of a statistical approach to those as well. As the failure databases improve and as the databases of existing tailings dams improve, that there would be more opportunity to do that sort of thing. And in the meantime, the way this will improve is through further discussion and collaboration with others in the industry. And I think with that, I'll wrap up, and hopefully I've left a minute for a couple of questions. Thank you. So yeah, I guess the idea is that we're trying to get these questions into the Q&A, which I think I can see. And if not, I think you could just unmute yourself and feel free to ask a question. Yeah, Paul, do you have a question?
Yeah, Mike, that was a really interesting presentation. Put you on the spot here a little bit, and that background isn't dams, but public water reservoirs, essentially dams, they fail much less frequency than tailings dams. If you had to point to one single factor of the factors you showed, design, governance, etc., which is there one that you would say where tailings dams fall behind publicly built, publicly maintained structures?
Yeah, well, I can take a crack at that, and Brad could probably jump in as well. Like my area of expertise is really in geohazard risk management, but what I understand is that, first of all, some tailings dams, in particular those built, with a downstream raise method, actually do have probabilities of failure that are probably comparable to water dams. But the other factor is that tailings dam is always under construction, and so its conditions are changing all the time. And I think that makes management all that much harder. A lot of water dams fail during first filling, and so that's my sense. But yeah, I don't know, Brad, if they've got anything more to add to that.
No, nothing else to add. That would have been my response as well, Mike.
Good. Well, maybe I'm learning something.